Hello, everyone, and welcome to the next episode of Math Talk. Today, I'm in California for a workshop on Koszul duality, and I have with me today Professor Wolfgang Soergel, who of Soergel bimodule fame, and who has done a lot of work on the topic of Koszul duality, in particular its relation to category O. So, welcome. Thank you so much for joining me.
Yeah.
Do you maybe just want to say a few brief sentences about the things that you're thinking about now for the audience?
Okay. I mean, I'm still trying to understand Koszul duality. But for this, I thought I should understand motives. And because I'm too old to understand motives, I'm trying to encapsulate them in a formal language so that I can use them without understanding them.
I see. So let's dig all the way back and figure out how we got here to trying to understand motives and Koszul duality. How did you first get interested in mathematics? Was there, did you start at an early age, or did it come to you a bit later on? How did that process go? How did you figure out you liked math?
In fact, I started out in primary school because my mother told me about the problem of the four colors.
Oh, really?
Yes.
Oh, really?
And I said, okay, let's solve this.
I didn't
manage.
Yeah.
It took me quite some time. And there was another problem about, the twin primes.
Right.
Which I also couldn't solve. So.
Yeah.
But I tried, and I found it amusing.
So already from a young age you knew, and then did this stick with you throughout like your primary school years? Like, did you have this idea that you would, were you always thinking you would go on to be a mathematician?
Well, I was a bit worried that if you study mathematics, then to get a professorship is sort of difficult.
Right.
And that to work would be more interesting as a physicist. So I started out to study mathematics and physics, both. And then it turned out that mathematics, I just could do it much better. I mean, sort of being not a very self-confident person, so I like the mathematics where you can sort of prove everything.
I see.
The physicists, they have to believe, and they have to assert, and
Right.
Yeah.
Yeah, I was very much interested in physics when I began, but the problem was for me is I didn't like the lab component so much. I mean, I wanted to go right ahead to the quantum labs, but first we had to drop marbles off of chairs and measure these things, and I wasn't so interested.
This was kind of the contrary. I mean, I started to study physics in Geneva. And because, in fact, my father is a physicist, and he worked at this big CERN lab in Geneva. There's a high-energy lab.
Oh, okay.
And so I started my studies there. And the lab was quite okay. And then we had a sort of funny way to learn things. So there was analysis and linear algebra. And then the physicist had decided that differential forms was it.
Right.
And so parallel to this, there was a course of differential forms, which was kind of a bit tough. I mean,
right.
A bit tough.
Right.
Sort of parallel to analysis 1.
Right. Yeah, that's a big step up.
Yes.
A big step up. Yeah.
And okay, I mean, I succeeded in the course, and I got even a present, a book by Arnold on classical mechanics. But then
this was a present for succeeding in the
course? This was a sort of a prize after this course.
Of course, that's a mathematician's idea of a prize of successfully doing mathematics. You get a book on more advanced mathematics. Yeah.
Yeah. Okay. I mean, this was physicists who did this.
Physicists. Yes.
The mathematicians wouldn't dare.
Yeah.
and then I said, okay, now I want to try to understand this really to the grounds, and it took me time. I still believe that differential forms is the good way to put it.
Right.
I'm absolutely convinced. physics.
Right.
And but not the way I learned it. I still remember. This was funny. They had a sort of a polycopier, sort of French. It was a sort of a scriptum, and I still recall there was sort of a whole big page filled by a big formula how differential forms and arbitrary variables and so on would change if you change coordinates.
Right.
So the formula fills the whole page, and below it was written, "We thus see that differential forms are independent of coordinates." I mean, I still recall I was pretty mystified by this way to put things.
So was it this goal of wanting to understand differential forms more formally that really started pulling you towards the mathematics? Well, you said you found you were just a better mathematician than a physicist.
Yes. I just understood mathematics better than physics.
Right.
I mean, it's a bit similar than my advisor Jansen. He told me, well, he did a theoretical physics too. Studied theoretical physics, and then he had to sort of discuss the two-dimensional representation irrep of SO3. You know, this is the kind of thing which exists in physics, but not in mathematics.
Right.
And so he thought, no, I'm a mathematician.
I see.
And
so sorry, he was your PhD advisor?
He was my PhD advisor.
Okay.
Also my advisor for my master's thesis.
So then, how did you connect with him though? Like, how did you decide that you were going to work with him? How did the two of you connect?
Well, first thing is that I kid Geneva. In fact, the faculty was very good. I mean, I basically understood everything. But then my parents moved away, and I thought, okay, this is working well. I should go to a famous place. And I tried to go to ETH Zurich. And then so I went there for some student counseling, and then they said, okay, I mean, you're very welcome. You should start again in the first semester and sort of redo parts of your high school examinations because it was not. So I said, okay, this is not a good idea.
I see.
And then I went to Bonn.
Okay.
Which was sort of a good place to do mathematics back then. I mean, this was Hirzebruch and these guys.
Right.
And I went to the second semester to Bonn, and this was sort of difficult because in Geneva I understood everything, and there I basically didn't understand a word. I mean, and in fact, well, it was some courses where I knew the thing already, and where I thought if I didn't know it, I wouldn't have understood a word either.
Right.
So I said, okay, that's a problem. I should
see.
maybe rather read books.
I see.
And so I started to mostly read books. This was the way. And Jansen was sort of this was less complicated, and I mean the seminar was sort of to the ground. And he's a guy who he really writes out little formulas and is careful to the ground, and I liked it.
I see.
And so I got to work with Jansen.
Oh, nice. Yeah. So you started working with Jansen. So I guess you were doing representation theory
of enveloping algebras.
Okay.
In fact, I didn't work on the problems he gave me. The first was on primitive ideals and power invariance, and this kind of thing was probably good. But but he also gave me some preprints, and I found a nice problem in one of these preprints. I think it was a course by Tony Joseph, and I could solve it, and this was basically my master's thesis.
Oh, okay.
Yeah.
Okay.
and it was nice. I managed to make it a little article, just 4-page article, because in Compte Rendu they only accept 4-page articles.
Oh, really?
Yeah. So.
Oh, interesting.
So I'm I got trained to condense my writing to the utmost possible. And I never get this attitude.
I see.
The last article I wrote sort of in the old style, where you really we have to, you type with a typewriter.
Right.
And then you put in special symbols.
Right,
and this kind of thing.
Right.
And it's an incredible work, even to produce a 4-page article this way. And then correct it and whatnot. I mean, boy.
Yeah. Yeah, I guess it's interesting to think about how advances like LaTeX even made it much more possible or feasible in order to even have the papers we now have today that are hundreds of pages.
Oh, absolutely.
Yeah.
I mean, I'm so grateful to Donald Knuth,
Yeah.
who put this. I mean, it's just a fantastic system.
Yes, yeah.
I'm now at 5,000 pages, and I'm this XDVI. I don't know who covered. I think he did it. Also, this XDVI program. I mean, it's just it's no problem. Yeah.
Right. Yeah.
In fact, much better than the newer program. If I'm trying to using this new PDF thing, it doesn't work anymore.
Right.
I mean, this old XDVI does the trick.
Yeah. So then you were doing representations of enveloping algebras during your PhD, and you mentioned during the lecture that you were at, was it a workshop, like a summer school towards the end of your PhD where there was this
much more serious. It was a whole. So I had finished my PhD.
Okay.
And then there was a problem how to go on, and then I got some German grant, and I went to Missouri for a year. They had a special program on representation theory for a year, which was, I don't know, there was Wilfried Schmidt and David Vogt and Dragan Milicic and sort of the whole. Dan Barbash. As I understand, I mean all of Harish Chandra's students in a way.
Right.
Yes. And this was for me really a fantastic opportunity. I learned decomposition theorem. I mean, I had before sort of tried a bit to do this kind of thing, but I couldn't get a foot on the ground. And now in this misery to learn all these things was fantastic and very difficult too. I mean, to get into the subject was really difficult.
But it's not much easier when you have someone to explain it, because I think, when we write up these things, of course, we want all the technical details to make sure it's precise. But when you talk to someone, you can say, they tell you, oh, you can just ignore this thing and you can think about it like this thing. And, they give you these sort of mental tricks in order to make the computations, right?
That's true. Yeah. And still, I mean, there were these lectures. Lectures were absolutely serious. Yeah. I mean, Dragan goes to the point. Yeah. I mean, David is more into examples. Yeah. He had lots of examples of funny representations, and then I try to read the books like Asterisk and whatnot, and trying to solve problem. I mean, the first problem. Yeah, I worked a lot on the problem of branch health. This was another. I mean, the problem is wonderful. Yeah, and I sort of managed to solve it by these new methods, and this was the first instance where I realized how powerful they actually are. Yeah.
So you came across that problem at this
absolutely at Missouri.
Yeah, and also you mentioned that this idea about the isomorphism between the two rings, that was a conjecture at the time, and that really caught your attention.
This triggered me. Yeah, I mean this was a preprint circulating. I mean Bailey and Ginsburg were not in this as far as I recall. But the preprint circulated. They had this preprint on mixed geometry, and this was fantastically beautiful conjectures. And so I worked on trying to figure out how this works. And this really got me triggered to this Koszul duality business, which I mean is due to this school. Yeah, and it came into being, I would say, from this preprint by Bailey and Ginsburg. Yeah,
and so that. That really gave you fodder for the rest of for a whole deal of your career then, right? That sort of launched you completely in this direction, and you just kept
Absolutely.
flying
I mean,
that way, yeah.
I mean, it was these conjectures, and then there was sort of a lucky strike to find a way to sort of get it proven. Because I mean, you have to prove isomorphisms of very complicated things, and I still sort of do not know the real reason. Yeah, I mean that's the problem a bit in this business. I mean, in the Langlands business for me as a whole. I mean, you have these two sides that you always check.
Right.
By combinatorics, and then by this sort of a bit more tricky methods. But I mean, I want a direct way. Yeah, this is not possible. That the reason is that the combinatorics on both sides are the same. I mean, clearly it wants to tell us look for the direct way why this is the same.
Right.
And I'm still not there. I hope Schultz understands it. But let's see. I'm worried that the true understanding needs methods that I cannot understand it myself. But let's see.
Yeah. So, well, I guess that I guess we already have an idea of what you're working on now, what you're looking for, towards the future. One thing I always like to ask in these interviews, maybe to switch gears a little bit, is and I think we got a taste of this already, is sort of your view of mathematics. So I think there's been like a lot of discussion, I've overheard and participated in here. Some people are very much, they're more about the ideas, right? The ideas are what's important, and somehow the details matter, but for some people, their real view of mathematics is the ideas, whereas other people, you mentioned you really liked how precise that Jansen was and how down to the ground. So where do you see yourself fitting in there? Has your view changed over the years in any sense about that?
Not so much. Not so much. I mean, I basically think mathematics should be simple. I mean, I strongly believe that the really interesting things are simple. Now, these gems are sort of rare, and to make a career basically to make a career, to make a living, we all work on sort of complicated things. I mean, which are not yet simple, or which, or maybe sort of some special roads. I mean, yes. I mean, I understand you have to explore the countryside and look at all the little roads and nice viewpoints and so on. But the most sort of important things, I think, should be simple. Should be sort of highways, which are maybe not yet laid out, but I have optimism they will be.
Well, we seem to be pretty good at simplifying things time and time again. So the problem is just every time we simplify things, we find a new way to complicate them afterwards. So
yeah, I mean, it's also, I mean, the problem with these simplifications is a bit that I mean, it easily happens that you say, okay, this thing is too complicated, I will simplify it, and then you have there a sort of a one-page calculation, and you simplify it to a 10-page argument, which in a way is, I mean, these easy calculations. Yeah, I don't like magic. I mean, I don't like magic in mathematics. I think it should be sort of evident if you put the right point of view. This is the dream.
Right.
And if it takes time to find the right point of view, takes the time. I mean, yeah.
So I think that already that last sentence there is an example of this last question I wanted to ask you. But so we're at the summer school with a lot of early career researchers. People who are, well, there's a span of people who are just starting their PhDs, some who have just finished. Do you have any sort of overarching words of advice for these early career students? Anything anything, that's maybe lessons you wish you had known earlier in your career that you want to impart?
Yeah, I would say in a way, early career researchers need quick results. To embrace getting down these big trees is not a good advice to early career researchers. They should sort of do doable things, sort of.
Right.
And there's lots of things to explore which are sort of not so fundamental. And I know also early or not so early career researchers which failed because they tried sort of too much to. I appreciate them absolutely, but if you embrace such big a problem and you cannot get anything out,
right.
Yeah. But on the other hand, I think if you have a tenure, you might a bit less sort of graze off the easy,
right,
the low hanging fruit,
right, exactly,
and sort of leave them to your PhD students,
right,
and try to go to things which are maybe less rewarding. Which means sort of better explain things which are already known and try to understand more complicated things.
Well, that's some great advice to leave off on, and thank you so much for chatting with me today.
Oh, you're welcome.
Yeah.